All right. So far, in past 2 days, we talked about the components of initial velocity of v naught, splitting up into vix and viy using the trig, right? And then we realized that horizontal velocity will not change throughout the whole trajectory because there's no acceleration in the x direction. However, in the y direction, my initial velocity in y is v naught sine theta, and this velocity will change as it goes up, and then it will slow down, slow down, slow down, slow down as it goes up, and then when it reaches the maximum height, the velocity in the y direction is zero instantaneously, and then it's going to speed up on the way back down. However, that happens because the acceleration in the y direction is caused by gravity. Acceleration due to gravity is negative 9.8 meters per second squared. So as you can see, the red arrows are acceleration due to gravity, and look at that, that never changes. It's always pointing in the negative y direction at 9.8 meters per second squared. All right. So the horizontal velocity will be the same as my initial velocity in x at any time throughout the whole trajectory. However, my velocity in y will change depending on time because of acceleration in the y direction. All right? So that's what we talked about. And then I gave you some equations here that can be be useful in calculating things for projectile motion. You have to treat the x and y direction completely independent of each other. Only common thing between these two dimensions is time. Time is the only thing that is common between those two dimensions. However, you could calculate x dimension completely independently from the y dimension at any time. All right? So that's where we left off. Now we're going to talk about a projectile motion of a special case where delta y is equal to 0. So what does that mean? That means my initial velocity, well, initial position, I should say, right? My initial position in y is equal to 0, and my final position in y is also equal to 0. So it starts at a 0 height and finishes at 0 height. So my initial position in y initial is 0, and my y final is also equal to 0. That's what this delta y equals 0 means, because final minus the initial is just 0. Okay? And this is a very, very special case because it does not work any other cases. When you're shooting from the top of a cliff, or when you're shooting it from below the valley on top of the hill, this only happens if you are shooting from a flat range on a flat earth, right? From 0 to 0. Okay? So you could think about maybe kicking a soccer ball on a level field to land on the other side of the field. That would be one of them, all right? Or artillery, firing a cannon from ground to ground, right? Flat ground, etc. Now, when we actually try to figure this thing out, we're going to try to figure out the range of this thing. This range equation is what we're going to try to figure out. So what is this range? Well, range is my delta x, right? My delta x is range. And that is the horizontal distance the projectile travels, right, in x direction. So if my x initial is 0, so here's my x initial position is 0, and here's my x final, right? This is my x final. We don't know exactly where that is yet. So x final minus the x initial is equal to delta x, which is the range, okay? And since x initial is 0, You could just think of x final as your delta x. So if x initial is 0, y initial is 0, your y final is also 0, then your x final is the range. And from the second equation in the y direction, you can say, okay, y final is equal to y initial. Obviously, y initial is 0, so we did not put the y initial there. But this actually came from this equation right here, equation number 2, okay, from page 2. So if you were to think about this equation, which was equation 2, y final is equal to y initial plus VIY times time plus 1/2 GT squared. Now we know from our previous page, this V naught can be broken up into VIY and VIX, right? And we know that VIY is equal to, right, V naught sine theta naught. So what we did was we substituted this VIY as V naught sine theta, okay? So here, my Y final is equal to, right? Y initial is 0, so we could substitute that 0 in there. Plus your VIY is V naught sine theta naught times t, right? Plus 1/2 GT squared. So what they did was they factor out the t from both of these terms because 0 doesn't matter what that is, right? So your y final is equal to t times, right, v naught sine theta naught plus 1/2 gt, okay? And since my y final is also equal to 0, if I set this equal to 0 and solve for time, my time is either equal to 0, or if I set this term equal to 0 right here, right, I get negative 2 v naught sine theta naught over g. So this is what we're going to use for our time. And obviously that makes sense because when your time is 0, your initial velocity, initial position in y was 0. And this time later, your final position in y is going to be 0. Okay? So this is the time it takes to go from here to here. Okay? From here to here is this time. Now we take a look at the second equation for, right? Second equation for my delta x. So basically, what I'm saying is we're going to use this equation right here. Okay? So this came from the second equation, right? X final is equal to x initial plus VIXT plus 1/2 a sub x t squared. But we know this a sub x is 0, so this whole term drops out to 0 because of a sub x. Acceleration in x is 0. So this VIX right here this Vix is equal to V naught cosine theta naught, right? So I'm going to substitute this Vix as V naught cosine theta naught. All right, so I should actually put zeros here too. Okay. Therefore, when I solve for x final, since x initial is 0, right? All I have to do is substitute this time right here, into my x equation as time. Okay? So what do I get when I do that? I'm going to get a mess, right? We already know the initial position in x is 0, so we could actually substitute this as 0 right here. So you know this is 0, right? So my x final now is equal to, ready? I have V naught cosine theta naught times this whole mess right here, which is negative 2 V naught sine theta naught over G. So when I consolidate this, I get this V naught times V naught, which is equal to V naught squared. Okay, so I'm going to make this V naught. This is also V naught. And this becomes V naught squared, right? Then I have 2 times cosine theta sine theta. They brought the negative down here at the front of G. So this is what we have left after all that mess. But there's an identity, there's a trig identity of double angle theorem of 2 sine theta cosine theta is equal to sine of 2 theta. So I'm going to actually replace this with sine of 2 theta. Then what I have is R is equal to V naught times, well, V naught squared times sine of 2 theta over negative G, where negative G is equal to negative of negative 9.8 meters per second squared. Therefore, this becomes positive. Okay? So negative G is negative of negative 9.8 meters per second squared. So, what is the significance of this? Well, if we were to think about sine function, right? Think about sine function, what it looks like. If you look at a sine function starts at 0, right? It starts at 0, and then it goes up maximum of 1, right? It goes maximum of 1, and then comes down to 0 again at pi, and then it goes to minimum of negative 1, and then goes back to 0 again. This happens at 90 degrees, and that value is 1 at 90 degrees for sine function. Okay? Here is 180 degrees. This here is 270 and 360, right? We're not worried about that. We're not going to worry about this. But let's think about the maximum value that happens for sine. The maximum value is 1, and it happens at 90 degrees. So since sine of 2 theta has to equal to 1, what must theta have to be in order to make it maximum value? Sorry, what would you say? Because I want to maximize this range. So only thing that can maximize this is what the theta is, because this v naught is constant because it's going to stay at whatever that you shoot it at. Acceleration due to gravity is constant. It's not going to change. You're not going to change the gravitational pull of the Earth. Only thing you can change is the angle, right? So to get maximum range out of this thing, what must your angle theta, your launch angle theta has to be in order to get the maximum range, maximum distance? Well, 90 would do it, but what theta would produce that 90? Because it's 2 times theta. Zach? 1? Yeah, I want 1. But what angle would produce that? Because it has to be 2 times the angle to produce 1. 45 degrees. Yeah. So the angle has to be 45 degrees to produce, right, maximum range, right? Because 2 times 45 will give you 90, right? So sine of 2 times 45 degrees will give you maximum of 1. Therefore, 45 degrees will produce the maximum range. So if you kick it or shoot it or throw it at 45 degrees, you will get the maximum range. Okay? So when you shoot this thing at 45, now again, this is not perfect. I'm going to just try to do my best to give, let's say you kick it or shoot it at 45 degrees. It will actually go to the maximum range like so. So this is 45 degrees. What would happen if you shoot this thing at 30 degrees? Would it go as far? At 30 degrees, it'll probably not go as far. It'll probably go like so. And then, let's say 15 degrees. At 15 degrees, again, it probably won't go as far. Okay, of course, these are all exaggerated. Okay. Now, what would happen if you go beyond 45 degrees? Let's say 60 degrees. What do you think is going to happen? You think it's going to go further than 45? No way. No way. Right? At 60 degrees, it will go higher, but land at its complementary angle of 30 degrees. And at 75 degrees, it would even go higher than that, but it won't go as far horizontally, but it would land at its complementary angle of 15. Is that good? All right. So like if you are like the artillery you know leader for Napoleon, right? And you want to make sure your cannons are effective. First thing you should do is you should know the maximum range of your cannon, how far it could reach. You know. Then once you know that maximum range, you could set your cannon hopefully less than the maximum range somewhere. Then, if you want to clear an obstacle like a wall, you want to shoot it at the complementary angle to go over the wall. Or if you want to go through the wall, you want to shoot it lower angle, right? So it's very effective. Not that I want you to start shooting walls down and stuff, but if you were Napoleon's general who's in charge of artillery, you got to know these range equations. All right. Hopefully that helps with range equation. Now, again, this is a special case. It only works on a flat ground when delta y is 0. This will not work on any other case except for this. Okay? All right. Any questions so far? So I think we talked about this in a classic blunder, right? If a bullet was fired horizontally from the shoulder of a tall man, and at the same moment it left the barrel, a second identical bullet was dropped from the same height. Okay? The key word here is horizontally. When it's fired horizontally, your theta naught, your launch angle, is 0 degrees. And that's very important. If it's shot at any other angle, this case is completely different. But it has to be shot horizontally, which means at 0 degrees. So when it is fired horizontally and dropped at the same time with the same bullet, okay, which bullet will hit the ground first? And common misconception will be, well, the one dropped because like the one's fired, it's got so much speed horizontally, it's gonna like go for like really. And the answer is no, because gravity will both act on both bullets exactly the same vertically. So if you shoot it with like a pea shooter, it's gonna go and then like hit like that. If you get it like 22 and then go right. If you get like 30-06, like greater power, you'll just go further, but it'll hit the ground at the same time. Matter of fact, only time when it did not hit the ground at the same time was when they had a gun so powerful, right? They had howitzers, like they were huge, like battleship guns back in the World War II. They're 16-inch, right, guns. They would hurl like 3,000-pound objects over 25 miles. So when they actually were test firing these guns, they realized they were missing their targets. And they were confused, like, I don't understand, it's not working. So these engineers were scratching their heads, and they brought it back to a physicist, of course. Says, how come this is not working? I don't understand why it's not working. And the physicist took a look at it for just 3 seconds and said, you idiots, you are living on flat Earth. That's why. Because the bullet went so far, it went beyond the horizon, right? So you had to calculate the curvature of the Earth. So as soon as they did that, guess what? They were deadly, right? So you could actually have a battleship like 20 miles around beyond the sea, shore. You won't be able to see these battleships because it goes beyond the curvature. But they could actually hurl like SUV size, no, not SUV size, but SUV mass, like 3,000, 4,000 pound projectiles. You'll see flashes across the horizon, and you see like these Subarus coming at you. It would just decimate a whole city. So they were deadly back then, and you can't even like see the battleship. So, of course, this has to be a flat ground. So you cannot be doing this on a curved ground like this. Okay? So I think we saw a video of this by Mythbusters. right? I'll put the link of the video on Schoology if you want me to. All right. So they will both hit the ground at the exact same time. All right. So I'm going to give you two projectile motion examples here, and these are very, very important examples. I would make these as your reference examples. Okay. So let's say a soccer ball is kicked from a top of 20-meter high cliff and is kicked horizontally with initial velocity v naught of 15 meters per second. All right, so here we have initial velocity v naught of 15 meters per second. And since it is kicked horizontally, my theta naught is equal to 0 degrees. Okay? So what's going to happen to this? Well, once it's kicked, as soon as it's kicked, it's going to be affected by gravity and it's going to actually start to fall, accelerate downwards, but not accelerate horizontally. Okay? So here's where it's going to land, right here. Now, this is x initial. This here is my y initial, and this is my y final. Of course, my y final is 0. My x initial is also 0. My y initial is 20 meters high because it's 20-meter high cliff. Right? So y initial is equal to 20 meters. So when we neglect the air resistance, it's going to behave, okay, as though time for this soccer ball to hit the ground will be exactly the same time as a soccer ball just being dropped straight down. Does that make sense? Okay. So we could probably find time because we know when this thing is shot horizontally or kicked horizontally, we know two things. First, the initial velocity of this 15 meters per second is exactly the same as your initial velocity in x. Initial velocity in x is the v naught because it is kicked horizontally, and that is basically 15 meters per second. However, initial velocity in y is how much velocity do we have in the y direction as soon as it's kicked? Good, like you said, nothing, 0. That is correct. Nice job. You guys brought your A game today. Yes. Because there was no velocity in the y direction at all when it's kicked horizontally. So initially, my velocity in the y direction is 0. And that's a very important thing to know. Okay? So let's write down everything we know in two different dimensions. Let's write down x and y. So I'm going to start with y actually. Okay, y direction on this side. And I'm going to do the x direction on this side. Okay, so if I were to look at y direction first, let's write down everything we know in the y direction. I know my initial velocity in y, v-i-y, is equal to 0. We just talked about that. I also know my y initial is equal to 20 meters, and my y final is equal to 0 meters. I also know soccer ball is kicked on earth, right? So my a sub y, which is equal to g, is equal to negative 9.8 meters per second squared. And I want to find time. This looks like a simple second equation. Equation number 2. Equation number 2 states, right, y final is equal to y initial plus VIYT plus 1 half a sub y t squared. Now I know that y final is 0, right? Y final is 0. So 0 is equal to y initial is 20 plus initial velocity in y is 0. So this whole term goes to 0. Plus 1 half times negative 9.8 times t squared. So here, if I bring this 20 to the other side of the equal sign, it becomes negative 20 is equal to negative 4.9 t squared. So if I solve for time now, my time t is equal to plus or minus square root of 20 over 4.9. If you don't see how I got this, come and see me after school. We'll have a nice heart-to-heart talk. So what is that if we do it? If we calculate that out, we have 20 divided by 4.9, and then take a square root of it, right? I get 2.02 seconds for my time. So it should take 2 seconds to hit the ground. So that was part A. Now let's take a look at the x direction for part B. For part B, I know my VIX, and my VIX happens to be 15 meters per second, because that is exactly the same speed as V naught. Now what? I know my x initial is equal to 0. I also know acceleration in x. What's my acceleration in x? 0. 0. That's very important. I know my time now. We calculated the time to be 2.02 seconds. I am looking for my x final. So let's take a look. I can use my second equation again, which is x final is equal to x initial plus VIX times time plus 1 half a sub x t squared. We know a sub x is 0, so this whole term goes to 0, right? We know x initial is also 0, so this term goes to 0. Here, my initial velocity in x is 15 times 2.02 is equal to my x final. So what's my x final? My x final is 2.02 times 15, and I get 30.3 meters as my x final. Is that good? Okay. Now for part C. For part C, they want to know what is the final velocity. They want to know what the final velocity is, the magnitude and direction of the soccer ball right before it hits the ground. So for part C, I should have moved this over to here. Sorry. Well, I'm going to put the C in between if I can, okay? Sorry. So for part C, okay, this soccer ball is going to be coming down, okay? And right before it hits the ground, it's going to have its final velocity like this. This is going to be my VF. I already know what the final velocity in the x direction is already. Why? Why do I know my final velocity in the x direction? Does my x velocity ever change? No. So my final velocity in x is exactly the same as my initial velocity in x, which is equal to 15 meters per second. That doesn't change. However, my VFY does. So my VFY is equal to blank. So if we could find the VFY, then you can just use Pythagorean theorem to figure out the magnitude of my VF. Then we can also calculate my theta final for the direction. All right. So what is my VFY? My VFY is equal to VIY plus A sub y t. We know the initial velocity in y is 0. We know that from up here. Right? And A sub y is negative 9.8 times time, which is 2.02. So what is my final velocity in y? I get negative 19.8 meters per second. So once I know these two components, I know 15, and I also know negative 19. So I can say my magnitude of my VF is equal to square root of, right, VFX squared plus VFY squared, right? So if we work it out, we get VF is equal to square root of, right? I have 15 squared plus, even though this is negative 19.8, if I square it, I know I'm going to get positive, so I'm going to say 19.8 squared. All right, so what is the magnitude of my VF? Square that plus 15 squared, and then square root that second. I get something like 24.8 meters per second as my magnitude of my final velocity. And then for theta is equal to, right? Now obviously this is in fourth quadrant, right? So this is actually my beta. But if you leave your theta as a negative angle, that works out too. That is simply tan inverse of, right? Tan inverse of VFY over VFX. And that is simply tan inverse of negative 19.8 over 15. That is equal to Whoa. Mine is in radian mode for some reason. It should be in degree mode. Hold on a second. I get 52.9 negative 52.9 degrees as my theta final. So I can finally say now the final velocity right before it hits the ground is equal to 24.8 meters per second, comma, theta final is equal to negative 52.9 degrees as my answer. Booyah! That's part C. Is that good? All right. Yeah, I will post these PDF format so you don't have to watch the whole video if you don't want to on Schoology, so you could actually have these up there color coded. Now I want to do one more example problem, and then I'll let you work on your homework problems afterwards. All right, so here we go. Now this looks like trouble because now we're kicking this at an angle. All right. We still have 20-meter high cliff, but instead of shooting it horizontally, it's being kicked at 30-degree angle. So my theta naught, my launch angle, is 30 degrees. Okay. So we know that this here, this is the V naught, obviously. And V naught is 15 meters per second as before. However, this V naught has a launch angle of 30 degrees. So I have my VIX and I have my VIY. And here's my theta naught as 30 degrees. So this thing is going to be shot out like that, and it's going to probably go, like so. Boom, right? Hit the ground somewhere. Now it asks, how many seconds will it take to hit the ground? Well, the first thing I would do is I would find the VIX and VIY on the side, just so we could have that ready. Okay? So let's calculate the VIX and VIY. So my VIY is equal to V naught, right, sine theta naught. So my VIY is equal to, right, 15 times sine of 30 degrees. That is 7.5. I think it's 7.5. Let me check. 15 sine of 30. Yeah, 7.5, right, meters per second in the y direction, right? Let's calculate now the VIX. VIX is equal to V naught cosine theta naught. So your VIX is equal to 15 cosine of 30. So 0.866 times 15, right? And I get 13 meters per second. That's my VIX. It's good to know these, okay? Because now I'm going to have to find part A. How many seconds does it take for sock ball to hit the ground? Well, we also know the initial velocity in x and y, but we also know the positions. So we know the y position, y initial is equal to 20, and our y final is equal to 0. We also know the x initial is also equal to 0. Right? We don't know what the x final is. We don't know what the x final is. So now that we know these, maybe we can split them up and then solve for time. So we know y initial is 0, 20, 20 meters. Your y final is equal to 0 meters. Your x initial is equal to 0. And your x final, we don't know. So these are all the things that we know from given. So for part A, let's use the y direction to figure out time. Okay? Let's write down everything we know in the y direction. Y direction. So we know our initial y position is 20 meters. We know our y final is 0 meters. We also know acceleration in y is negative 9.8 meters per second squared. We know velocity initial in y is equal to 7.5 meters per second, and it's positive 7.5. And I'm looking for time. Okay? So it looks like we should use the second equation. Y final is equal to y initial plus VIYT plus 1/2 a sub y t squared. All right. Well, let's write down everything in here and put it in. Y final is 0. Y initial, 20. Plus initial velocity in y is 7.5 t plus 1/2 times negative 9.8 times t squared. Hey, this looks pretty familiar. This looks like 0 is equal to negative 4.9 t squared plus 7.5 t plus 20. How do we solve for time? Is that? Yeah, you could factor it, but factoring is going to be pretty tough because of these numbers. But you can use the quadratic formula. Yeah, you asked yourself when you were taking algebra, when are we going to ever use this? Well, here it is, right? Here it is. So since quadratic formula is a real pain in the butt, you should program this into your calculator. Or you could just look it up online, right? If you look it up online, you can see, let's see, if you just type in quadratic formula and you could just type all that in, right? So if you just type in quadratic formula on your calculator, on your thing, and you could just click any of these, right? And then you could just type in, oh no, I don't want that. Math Papa. Here you go. Right here, coefficient A is negative 4.5, or 4.9, sorry. And then coefficient B happens to be 7.5, right? And then coefficient C happens to be 20. And you hit calculate. And we have two answers. We have two answers. And one of the answer is negative, one of the answer is positive. So T is equal to, right? I get 2.9 seconds, or negative 1.395 seconds. So obviously we should select the positive time, right? We should select the positive time. So it does take 2.93 seconds to hit the ground from 20 meters above the cliff, kicked at 30-degree angle at 15 meters per second. All right. And then part B asks, how high from the base of the cliff will the soccer ball reach? Well, they want to know how high it goes from here to here. H max. Well, I know from here to here is 20 meters, right? So if we could calculate your Y max and then add 20 to it, you could figure out your H max. Does that make sense? Right? So for part B, let's calculate your Y max. So what happens to my velocity at Y max? When it reaches the maximum height, what happens to my velocity? Do you remember? When it reaches the maximum height, what happens to my Y velocity? Zero. Absolutely correct. Zero. It's right. It instantaneously stops in the Y direction before it comes back down again. So that's good to know. Vy max is equal to zero. We also know initial velocity in Y, which is 7.5 meters per second. And A sub Y is equal to negative 9.8 meters per second squared. And looks like we have enough information to figure out what my Y max is. We can use equation number 3, which is VFY squared is equal to VIY squared plus 2 A sub Y delta Y. Delta Y is the Y max. So VFY, 0, that's the Y max. Square that, you still get 0. VIY is 7.5. Square that, you get something big. Oh, sorry. Thank you. Right. Plus 2 times negative 9.8 times Y max. So 0 is equal to, right, 56.25, that's 7.5 squared, minus 19.6 Y max. So my Y max is equal to, I get 2.87 meters. So it's going to go up 2.87 meters from where it's kicked. So my H max, oops, not hex, H max is equal to 20 meters plus Y max. Therefore, my H max is equal to 22.87 meters as the height from the base of the cliff. Then for part C, I'll give you time to catch up. That's from chapter 2, equation number 2, equation number 3 from those constant acceleration equations. Yeah, that's not written on there, huh? Maybe we should write that down just so we could have it. Yeah, so we could actually use third equation, Vfy squared is equal to Viy squared plus 2g delta y. That's the third equation. Alrighty, alrighty. What about C? How far away? Well, we know a few things. We know Vix is equal to 13 meters per second. We also know initial x, which is 0 meters. We know a sub x is equal to, what's my acceleration in the x direction? 0. That's very important. And I know my time. My time is equal to 2.93 seconds. And I'm looking for my x final. Therefore, I can use my equation 2 again, which is x final is equal to x initial plus Vix plus 1/2 a sub x t squared. You know a sub x is 0, so this whole term goes to 0. So here, my x final is equal to x initial is 0 plus 13 times 2.93, right? So what's my x final? So 2.93 times 13. And I get 38.1 meters as my x final. Are we okay with that? Now we need to do part D. No, we did part, no, part D, yeah, what is part D? Final velocity, right? What is the final velocity, magnitude and direction of a soccer ball at maximum height? At maximum height, so here, at maximum height, right, at this location, right here, at maximum height, what velocity do I have? How much do I have in the x direction? How much do I have in the y direction? Y direction is easy, 0, right? So that's easy. So y direction, 0. What about x direction? 13, correct. I only have the VFX, which is 13 meters per second. So my final velocity at y max, right, is equal to 13 meters per second, 13 x hat, plus 0 y hat meters per second. That means my final velocity at y max is basically 13 meters per second, and the angle is 0 degrees. That was easy because my y velocity is 0. So if I square that and square this, add them up, square root it, it's going to be 13. And since it's only going in the x direction, it's 0 degrees. Now for E. I'm going to run out of room, so I'm going to have to write in the back of it. So I hope you guys can follow me on that. Is that okay? All right. So here, if I were to do E, we know the final velocity is going to be that. We also know the horizontal velocity will remain at 13. So Vfx is equal to Vix, which is equal to 13 meters per second. That we already know. And then here's my y final. Vfy is equal to question mark. So I should make this easier. Make it look like it is. So once we know Vfy, we know Vfx already, so we can use Pythagorean theorem to figure out the magnitude of this, and then calculate the angle theta final before it hits the ground. So we can say, right, Vfy is equal to Viy plus a sub yt. We know the Viy happens to be 7.5 minus 9.8 times t, which is 2.93. Right? That's my Vfy. So my Vfy is equal to, so 2.93 times, right, 8, again, negative 21.2 meters per second, right, as my Vfy. So my Vf is equal to, right, 13x hat minus 21.2 y hat meters per second, right? So the magnitude of my Vf is equal to square root of 13 squared plus, again, if I square this negative 21.2, it's going to get positive anyway, so I'm going to just leave it as positive 21.2 squared. And that is equal to, right, square root of 619, right? And that is equal to, I get 24.9 meters per second as the magnitude of my final velocity. Therefore, theta final now is equal to tan inverse of, right, Vfy over Vfx, and that is equal to tan inverse of negative 21.2 over 13, and that is equal to negative 58.5 degrees. So I can finally say my VF right before it hits the ground is 24.9 meters per second, comma, theta is equal to, theta final is equal to negative 58.5 degrees as my E. Whew. All right. Is your brain full yet? Yeah? That was a pretty like intense lesson we had, right? It was a pretty intense lesson. So I will end my video lecture here as of today, and rest of the period, I'll let you work on your homework packet. Okay? In your homework packet here, make sure you read them carefully, and I will go over all these homework problems, or try to go over most of it on Wednesday and Friday. All right? All right. So I'll stop. Any questions?